we have array with numbers, and we want to move from 0 position to the end position. We allow it to move for adjacent cells, and also allow it to move if the current cell is prime, to all the cells that are divisible by this prime, like x divisible by prime equals 0. So we can jump to this cell and then reach the destination. The breadth first search is trivial idea, but the primes is not trivial. So how to navigate this? First, we can prepare the primes. So we can take all the possible range of, so from 0 up to the maximum. This would be the range, and we want to find primes in this range. For this, to find the primes, we use sieve, and this is just 2 for loops from 2 up to some n, and then inner loop for this is I, and j is like multiplications from I times I up to n step I. So it's kind of, we're taking all these numbers from this range, and then we check, and then we just say this is a starting point, and then we do this step plus I. So for example, for the 2 I equal 2, we're going to take 2 plus 2, this 4, 6, 8, and so on. Then I became 3, and we say 3, 6, 9, 12, and so on. And inside this loop, we say that prime for this I for this I times j equals false. So let's look at the code. I kind of can make a mistake now. So yes, so it does it like it's the same. So for my case, when I write it like this, it's just prime j. Now okay, we have all the primes, but what can we do with them? We still have to know for each value inside this array, we want to know what all the primes it can be reachable from. So for all the primes, so for a particular value, we go from all the primes being primes, and we check if value divisible by prime. And this is all of n squared, and this wouldn't be accepted. It will give you time limited exceeded. Now, instead of checking it for all the primes and all the numbers, so it's for v, so that means for v inside an array, we can do the opposite. We can factorize. So step 2, factorize. Step 1 was priming, and step 2 is factorize. So we have number v, and to factorize we are doing this kind of tricky algorithm. Let's look at it. I'm not very fluent in it because it's not very frequent algorithm in lit code, but still let's look at it. So we doing iterations, some number from 2, then we expecting this I squared, or maybe like this, I squared less than x is less than v, I would say. And then we say if this is a while, of course, while I plus plus, and inside it we looking if this v divisible by this I. So we're checking all this range I from 2 up to some number, I would say square root of x of v, like this. And we're checking if v is divisible by I, and also if I is prime and I is prime. So basically we're looking if this v is divisible by prime. And then if it is, we adding this as factor. So we adding this I as a good factor, so plus I. And interesting step is this kind of while extra loop. So we decreasing the v, decrease v. So instead of just checking all the i's for this range, we shrinking this range by v while v divisible by this prime. We are doing shrinking it to the smallest value. So v divisible divide equal by I. So for example, if v equal 10 and our prime is like 2, or maybe let's make it no 10, 12, prime is 2. So the first we say that 12 divisible by 2. Okay, we adding this 2 to our prime list, and then we're dividing our v, so we don't keep it like 20, so it becomes 10, and then again it becomes 5, and 5 is not divisible by 2. and then we stop and go into the next prime candidate. So this is how factorization work. I didn't familiar with the algorithm, that's why I didn't solve this problem myself. Now after we done this, we for each v inside array, the prime factors are very small prime factors, very small list of numbers. So small, so we can store them, and this solution is less than O n squared. It is O of n, maybe for each n prime factors is like square root of v, so maybe it's like this. I'm not sure, because the square root of v, not n, so I would call it like this. Now we have basically we have a list of primes p1, p2, p3 that can point to this v. We can put it in a map, so basically group by prime, so p1, and point it to some position i1, i2, i3, and so on. And so for p2, this is basically hashmap. J1, J2, and so on. Basically, now we can say if some value is prime, we can look at this hashmap and find all the indexes that are reachable from this prime. Because of this preparation step. Now this is how hashmap preparation looks like, and after that the breadth search is trivial algorithm. You just use deck at the first step, count steps, iterate the queue size, remove markers visited, look for the left, right, and look in the primes. So, and that's it. Now let's look at more interesting version of this algorithm. It actually can be improved or optimized. So in the final version, I didn't use this extra hash map. Yes, I calculated this prime table. I called it S, but S is just boolean if it's prime or not. So initially it is all true except first two variables, and for all multiplications I set it to false. And then inside the depth search itself, I check if the current value is prime, and it's not visited prime group yet. We iterating from this prime, we iterating forward by step of this prime. So we are looking of each prime multiplication. So basically the J would be every number that is divisible by this prime. So instead of factorizing these values of n, we are iterating over factors of this prime. It doesn't matter if these factors are inside this array. Then we check this n is a group by, and means if we have this number actually in an array, and then just put it to the queue. Now the rest is the same. It is interesting that Rust has the group map by, that's similar to Kotlin group by, that gives you this hash map. And yeah, this is all the same. It still does this step by, and filter map uses sum and flatten. So that's it for today.